Hi, and thank you for the nice introduction, Elisa, and welcome to this session. As Elisa said, my name is Chiara, and I'm a machine learning engineer at Stream, where we build chat and activity feed components that our customers can use to easily add chats and feeds to their product without having to spend months building a whole chat infrastructure from the ground up. And the focus of our team is primarily on chat moderation. In the past, we worked on detecting toxic and explicit messages, and currently we're very focused on commercial spam. And the talk today will be about commercial spam. Before I begin, I want to give a shout out to my dear colleague Bhaskar, who is hanging out in the chat, ready to answer questions. So feel free to ask any questions during the presentation. And I will also hang out afterwards in the QA booth to answer your question that you might have after the talk. So feel free to join us there afterwards. So the talk today will be about how we can use natural language processing to identify commercial spam. So why do we want to moderate contents in a chat? Stream provides a lot of chat solutions that are used in very diverse communities, from live events like this to online marketplaces or gaming apps. We can imagine that with so much user-generated content, it is really important to stop bad actors from the start because we want to create a healthy environment for all our end users. So we need to keep updated with all the possible harms that can occur in a chat. And we also want to moderate messages fast so that harms cannot reach a lot of users. And this is why we need AI moderation. So we cannot put this all on human moderators. We want to build solutions that can handle a large volume of messages and a large volume of users. And so as I said before, the talk of today will be focusing on commercial spam, which is a type of harm, like many other harms that can happen in chats. Commercial spam is very repetitive content that aims to promote or advertise or direct recipients to perform a specific action. So for instance, it can take the form of asking users to visit some URL or repeated mentions of products or people or companies. It is something that users really dislike because typically it disrupts the focus of conversation, and usually spammers have a high volume of messages. So it's something that really distracts users and gives a very bad user experience. So it can also cause a loss in revenue and churn for our customers. And this is why we want to target this. So what we have seen so far, like the simple solution are to use regex expressions. So for instance, we might want to filter out words that appear in a block list, like some common words that you can see in spam messages, such as click here or visit this URL or buy this product. The other thing that can be used is to look at the user volume. So check if a user has sent many messages in a short amount of time. But what we have seen is that users, spammers, get really creative to bypass these filters. So for instance, to bypass regex, they can switch out words. They can be very smart doing this. Like user volume can also be faked by opening multiple accounts. So this whole thing becomes a whack-a-mole game, basically, where every party tries to stay one step ahead of the other. So we wanted to take this a step further and try to find a more robust solution to discover spam messages. So we decided to focus on two main things. The first one is to check whether a message has been sent many times, which is really the most obvious property of a spam message. And the other is to try to identify what is the goal of a message based on the text. So in this presentation, I will try to show you what are some challenges that we've encountered in these two approaches and how we overcame them. or we are still doing it, but I mean, so let's start with the repeated messages. So this is something that is in principle easy to find out. You just query a string, and it's really easy to check how many times a message has been sent if the message doesn't change. But what spammers often do is that they change little parts of text, like these two messages here. So yeah, here is just some numbers that have changed. So in this case, just querying the string doesn't work anymore. We need to do some more advanced deduplication. There are some techniques that are really widely used, such as calculating a Levenshtein distance. In this case, we want to see how many insertions and deletions you need to do to go from one text to the other. Another metric is Jarrow-Winkler, which is similar. So you can see they work pretty well. The score is almost 1, which means that these two messages are extremely similar. But what happens if the spammer changes the message a lot? So in this second case, you can see that the second message is actually very similar to the first. We can understand that it's the same message. They're trying to promote this Investing Coach Unlimited software, and they're sharing what is the discount. So the information is exactly the same, but the message has been written in a totally different way. So by just comparing the strings, we will not see that these two messages are duplicates. So the Levenshtein distance, you can see that it's less than 0.5. So this means that they're really different from each other. So yeah, this is the first problem that we encountered, and I will go back to this later. Now let me talk about the second feature of spam messages. So we wanted to see what was the flavor of the message, the purpose of the message based on the text. And to do so, a very powerful way to do this is to use transformer-based models. The most popular is BERT. We also used it. We actually used knowledge distillation, which is a simpler version of BERT, because I want to remind you that our focus is chat, so this needs to be very fast. We need to be able to have results of our model in a few milliseconds, so that's why we needed to use simpler models. This model is performs a classification task, so this is supervised training. And to train the model, we need a lot of training data. The most obvious way to gather this data is to use public data sets. We also did this at the beginning. They're fantastic because they're readily available, already labeled. We don't have to do a lot of effort for this. But unfortunately, they're not very representative of our data. Chat messages evolve a lot, so even data that is 5 years old or 2 years old maybe can be completely different from current data. Also, the definition of harms is not exactly the one that we want. So yeah, we wanted to have something that we could control more. Also, this data can be very noisy. So with our own data sets, we can have full control over what type of messages we want to include in the model, what is the labels that we want to use. But the downside is that we need to label a lot of data. To do so, we launched an internal message labeling competition. We built an app, and our colleagues were really eager to label messages to train this model. We managed to label thousands of data points. So first problem was that there was a lot of work for this, and this solution was not really scalable. We needed way more data. And the other was maybe even more important, was that there were a lot of disagreements. So we started with a very broad definition of spam, which we then refined, but there were about 20% of messages that had conflicting labels. After that, we refined the labels. We tried to use more specific definitions, but still we had a lot of disagreements. So we wanted to find a solution for this. And you can see, if I put some example of messages, sometimes it's very hard to know, to tell if a message is spam or not. For instance, hi, my lovely friends, it's my favorite day of the year, my dad's birthday, so I'm giving amazing discounts today. Check out my account and give me a follow. To be honest, I don't know whether this is spam or not. It really depends on the context. So what we tried to do was to extract the groups of messages. So we decided to, instead of looking at each message by itself, to group these messages into groups that had similar flavor, similar intent. For instance, these messages, you can see that they're all users trying to promote their profile. So if you can group these messages, then it's way easier to make a decision. So to do so, we used sentence embeddings. If you work in data science and you're familiar with NLP, you probably know word embeddings. They're a way to represent words with vectors, so they can be used by a model. So each word is associated to a vector in an n-dimensional space, so we can do operations with them. There are very simple models such as word2vec or more advanced ones like BERT. But in this case, we wanted to go one step further and use sentence embeddings. So with sentence embeddings, we have a vector that represents a whole sentence. And let's see how this can help us. So the interesting thing with this approach is that if you have points associated to sentences, you can have distance metrics. And you can know what sentences are similar to each other and what are not. For instance, these three sentences. If I look at the first two, feel free to write your questions in the chat, or if you have any questions, feel free to write them in the chat. String-wise, they're pretty different, but have a very similar meaning. So I can calculate the cosine similarity in this space after I get the embeddings, and I can see that they're really similar, so they're 90% similar. If I take a third message, such as visit getstream.io, if you want to know more about this topic, you will see that the cosine similarity is way less. So let's see how this helps us solving the two problems I mentioned before. So to spot repeated messages, remember the first two messages that I showed you before? These were about an investing app. They were written in a very different way. And the Levenstein distance was less than 0.5, but in this case, the cosine similarity is almost 1. So we have a proof that even if we rework the sentence, the messages are considered the same. And we can consider these two as duplicates. And this really helps because now we have a lot of machine-generated text as well that spammers can produce to bypass the filters. So it's not only a simple regex manipulation, but we do paraphrasing and this kind of more complex operations. Excuse me. And by the way, we have a nice presentation by my colleague Neha, who gave it in a previous edition of Dev Week. And I put the link here so you can visit it and watch it if you want. So how can we do this? I'm sorry. So if we have these points in space, we can run clustering algorithms. And we did a very simple one. We use community detection to group these similar messages together. So in this case, we can find clusters of messages in a very efficient way. And clusters will be something like these 4 messages, which will be duplicates. So yeah, as I said before, we can catch these duplicates even if they are reworked in a very different way, if the meaning is the same. Of course, you need to play with thresholds here to not have too many false positives, but such an algorithm can help a lot. And the other point of this, which I didn't touch yet, is that it's very fast. So in this case, we're not comparing strings to string anymore. We are not looking at all the possible operations that you need to do to transform one string to another. In this case, we're just comparing vectors and calculating distances. So we can store them as vectors in a space without using too much memory. And we can also calculate distances efficiently. So for instance, Levenstein distance, here I put the time in seconds that it takes to duplicate a list of n messages. And you can say that even with less than 10,000 messages, it takes more than 10 minutes to calculate Levenshtein distance. Whereas with cosine similarity, it's way faster, and community detection using cosine similarity distances is really efficient. It even scales better. And the other use case is to compare one message against a list of messages. So this is actually the most common case that you would encounter when moderating messages, because we will have an existing cache of messages, and we're going to compare a new message to the cache to check if there are duplicates existing. So in this case, we still have a linear scaling. With Levenshtein distance, it still takes quite some time. This time decreases by 6-7 times by using cosine similarity, and even more with semantic search, which is a more efficient way to do it. Sorry. Yeah, so the other point was how to identify the intent behind the messages. So we were stuck at the data labeling stage. So we had disagreements, and we couldn't label a lot of data. So let's see how these embeddings can help us with this problem. So what we did was to calculate embeddings and do a hierarchical clustering. We tried several approaches, and at the end, we decided that hierarchical clustering was the best for a use case. And I plot here the UMAP embeddings. So this is just a 2D projection that allows us to see the points better. And this is just a few thousands examples from our chat database. So you can see these clusters. And for instance, here we have something like people asking for measurements. So what is the heel height? We have, can you measure the insole length, please? Or are they 14.5 centimeters wide? These are all very different messages, but they're still part of the same cluster. And we can easily label all of them. I mean, this is clearly not spam. So if we know what messages on a cluster are, we can easily label them. And another is, for instance, users sharing their profile. So here we have all users who want to share the LinkedIn profile. In this case, it was not clear if this was spam or not. It depends on the context. So this called for more informed decisions. So in general, we were able to gather all these points and cluster them, and then take more informed decisions based on the actual content of each cluster and more context. And to help us take faster decision, we use name entity recognition to give cluster the names. So for this, we extracted the most common verbs, words that were part of the cluster, as seen as a corpus of text, and we extracted these names. Sorry, they are not perfect, but they definitely helped to understand what was the content of each cluster. And there are other ways to do this. Maybe in the future we will have better ones, but this tremendously helped. And now I want to show you how this improved our model. So here I plotted the results of the models, of the model metrics. We have the area under the curve, F1 score, precision, and recall. And it's represented as improvement compared to a baseline. So in light blue, we have our original model, which we call Megamod model as a nickname, because it embraced a lot of harms. So in this case, we had an improvement, but it was only when we started to focus on spam data that the results improved more. But here you can see in dark blue what happened when we introduced our own data set. So in this case, we had an improvement of more than 60% in all metrics. I want to I want to stress again that we didn't use sentence embeddings in the model itself. We still use DistillBERT because this is something that has been heavily tested. We know very well what is the inference speed and the load it can bear. We have an inference time of around 10 milliseconds average per message. So this is something definitely viable for a chat usage. We are not guaranteed to have this with sentence embeddings, but it's not excluded that we might use them in the future. And yeah, as conclusion, it was definitely worth to spend time labeling all this data, but it was also worth it to do it in a smart way. Using sentence embeddings allowed us to accelerate our data labeling. So we went from involving people for weeks to labeling data in hours. So this definitely helped us not only to get more data, but also to get more accurate data. We were able to take more informed decisions by taking decisions based on a whole cluster instead of per message basis. And also because our data labeling was faster, we could have more opinions on a single message. So this also reduced uncertainty. And the other point is the other feature that we can use is to look at how many times a message was sent. And this way we could spot duplicates faster and also more accurately because we can bypass certain creative ways to rephrase messages. And also, yeah, this is something that is way more efficient because you can store vectors instead of strings. And as a next step, we will definitely expand our training data to gather more use cases, more types of apps, so that we can better identify harms. And another very useful thing is to identify spammers. So use the the spammer behavior to directly flag users instead of messages. So this would remove bad actors from the start. And why not? We can use this topic modeling that we did to discover new types of harmful messages. And with this, I would like to say one more thing, that if you find this problem interesting, I would like to let you know that Stream is hiring. So we're looking to expand our moderation team. So feel free to reach out to us. I put my email here, but you can also visit the Stream website, getstream.io, for more information. And I'll be hanging in the QA booth after this talk, so feel free to reach us there. We will post a link in the chat. And thank you very much.